Okay, so you'll be bursting with anticipation that we're at last getting to Erdös's theorem, which I've been quoting so often in this course. That's what it says. You can have, in a single graph, arbitrarily large girth and chromatic number at the same time. So for every k, for every integer k, no matter how large, there exists a graph that has chromatic number and girth both bigger than k. Right, so the approach to prove that, Erdös's approach, since these graphs or such graphs are so notoriously hard to construct, was the probabilistic one to prove that in a suitable probability space, the measure of those graphs that fall short of what we desire is less than 1, or more precisely, the measure of those graphs that have short cycles is less than half, and the measure of those graphs whose chromatic number is at most k is also less than half. So since less than half and less than half don't add up to 1, there must be some graph that those sets are missing, and that will have both properties. So that's roughly the idea, and we know a little more now how to define these probability spaces. So we'll be working in let me say proof idea first. In G of NP, where this P is not going to be constant, but will depend on N, we want to prove find the definition of P and some N such that the probability that we have short cycles will be cycles of length at most k today, right? So those are the ones we don't want. So the probability of the girth being at most k is less than half, and, well, the probability that the chromatic number is at most k should also be less than half. Now, it's a little tricky how to come to grips with that property. And we'll do something instead, which is enough, and we'll just say that it's unlikely that there are large enough independent sets to make the chromatic number small. Okay? Small chromatic number at most k, which we don't want, will require that at least one of the color classes is big, namely at least n over k, and so we'll make that unlikely. So the probability that alpha is at least n over k shall also be less than half. That's the idea. Now we're free to define our P, and it turns out that the obvious conflict of aims here seems to deal us a fatal blow right at the start. So what's the conflict of aims here? In order to make it unlikely that we have short cycles, we want few edges. Right? So we want P to be small. In order to make it unlikely that we have large independent sets, we want lots of edges. So we want P to be large. And unfortunately, the threshold for both is exactly in the same place, namely at P equals 1 over n. Right, one can prove, and we'll prove that next lecture, that, one needs P to be less than, so let me write this informally, need, for one, we need P to be less than 1 over n. So more precisely, P is little o of 1 over n, for those of you that have seen this before. So we want P to be of a lower growth rate than 1 over n. So I'm thinking of 1 over n as growing, which of course is a little counterintuitive, right? It should grow even less than 1 over n. And for 2, we need P to be bigger than 1 over n. So P will have to be big omega of 1 over n. All right, so 1 over n is big O of P. So this is bounded away from 0. Right. P divided by this is bounded away from 0. Unlike here where it tends to 0. Okay. Notice that, well, not notice, but we shall also prove next time that when P is indeed little o of 1 over n, so smaller than 1 over n, then not only do we not have cycles of length at most k, as we're trying to forbid, but we shall have no cycles at all, which is not really surprising because k is a constant, and the k didn't seem to feature here very much. So it may be unsurprising, and indeed it is true, that for this growth rate, for this P, we shall have almost surely, and I'll tell you what exactly that means later, no cycles at all. Now, if we do have no cycles at all, then the graph is a forest, most likely, almost surely. If it's a forest, the chromatic number is going to be 2, and it'll have large, very large independent sets. At least half the vertices will have to be independent from one color class. And that will be really large, n over 2. So we have a problem here. And that's the point where the likes of us that are not Erdös might give up. Not so Erdös himself. So he said, okay, we can't sit on the fence at P equals 1 over n forever. So let's come down one side of the fence and see what we can do. We're coming down on the side of trying to make large independent sets unlikely by allowing just a few more edges than 1 over n. Okay, so idea, choose P of n slightly bigger than 1 over n, so that we don't have too many short cycles. Almost surely. That will get a precise meaning later. I don't need it yet. There are at most half n short cycles. Okay. Why is that still good enough? Since we're coming down on the side of making large independent sets unlikely by allowing a little more than 1 over n edges, whatever we get will certainly not have big independent sets, so that will still be satisfied, since we are bigger than 1 over n. And we'll have a few short cycles. We don't like them, so we're going to kill them off. How? Well, we could delete an edge from each one of them, but that'll make it possible that we suddenly have large independent sets, which we didn't want. So we'll kill a vertex. And we'll have only n over 2. We'll only have half n short cycles. That's tiny, right? Remember, what is the sort of the number you would expect? I'm trying to avoid to say the expected number. What's the number of short cycles you expect? So it's k cycles. How many k cycles, potential k cycles, are there on n vertices? Something like n to the k. Right? So that is rather less than n to the k. And we can afford to kill one vertex from each of these half n cycles and still have some vertices left, which is good news. And indeed, we'll have at least half the vertices left. So that is not going to go up by killing vertices. We are not going to have large independent sets if we have fewer vertices. Larger. So that will still be true, except we want large in terms of number of vertices divided by k. Since we only have half the vertices left, we shall have to insert a half here, so that we'll still, even after deleting half the vertices, have no large independent sets, even compared with half n rather than compared with n. So that's roughly the plan. And then in that other half, there won't be any short cycles, and there won't be any large independent sets, so the chromatic number is also going to be big. Right? That's the proof idea. Now, what is slightly bigger than 1 over n? By a factor of n to the epsilon. Right, so this is something like, if epsilon by universal theorem in mathematics is always small but positive, so n to the epsilon is something like root n, where you have higher roots as epsilon gets smaller. So this is something that goes to infinity, and that's what we want. We want to grow faster. We want to be bigger than 1 over n. So we'll put a factor of 1 to the epsilon in front of the 1 over n, and that will be our p. How do we choose epsilon? It doesn't matter how small it is. So the proof will work with any epsilon that is that we need, as long as n is big enough, and we'll be happy for. In fact, we shall not just find one n, but we shall prove that whatever we do will work for all large enough n. Right? That's easier than coming down to define one particular n. We take all large enough ones that satisfy this, all large enough ones that satisfy that, and the intersection of all those large enough ones is still large enough. It's still all large enough for some larger definition of large, so that'll be fine, and the epsilon will be free to choose, and we'll make that dependent on k. Right? So, plan p will grow slightly faster than 1 over n by a factor n to the epsilon. Epsilon, in order for this to work, can be as small as we like, and what we like is 1 over k. Well, we'll see that later. Okay. Okay, we need a lemma. I'll just give it a number 1121. For k, positive k, and p at least 16 k squared. The point is that this is a constant, right? Rather than, it's less than n to the epsilon, no matter how small epsilon is. That's the point here. Times 1 over n. So for all k and this probability, we have that the probabilities that alpha is large and here, for the reason I mentioned earlier, we're a little choosier. We count as large something only half the size already than what G will be like, in order that the other half will still be large. So that goes to 0 as n goes to infinity. Right, and that's just calculation. It's easy. You can read it in the book. You don't have to learn it. And yeah, the point is that this is a constant, and therefore we shall have p of n at least n to the epsilon times 1 over n, which is going to be bigger than that, and whenever we're bigger than that, this will hold, and that's what we shall need later. That's why we need the lemma. Okay. So, let me start the formal proof of Erdös. We shall choose epsilon first, and then when we've done that, we'll choose p in terms of epsilon, and I've indicated both already. So let epsilon be 1 over k, so k is given, right? And p, or p of n, to be n to the epsilon times 1 over n. I'm writing it like this rather than n to the epsilon minus 1, so as not to hide the reference function here, which is 1 over n. And we're bigger than that by n to the epsilon. So that's how we're choosing k, and p, so let epsilon be smaller than 1 over k, just for good measure. But of course, epsilon, as all epsilons, is always positive. Okay, so now we want to show that there are, well, not that there are no short cycles, but there are only few short cycles. So let's count the short cycles and then prove that the expected value of that count is small enough to make the probability small by Markov. Okay, so let x be the random variable that counts the short cycles. So right, that's just x. And we want to use Markov to show that the probability that x is bigger than we want, more than half, more than half n, right? We want the number of short cycles to be small, less than half. So we want the probability that there are at least half n short cycles to be small. And we want to use Markov for that. So the little a in Markov is going to be half n. All right? Okay, so let's compute the expectation. So that we had lemma 1114. What's the expected number of short cycles? Remember that? So we have the expected number of k cycles. Let me write it down first. So it's at most half n to the k, p to the k. And that came from, so this, oh, sorry, half k. Doesn't really matter very much. These things are all constants, so, but never mind. So we're counting, if we're counting the I cycles for I from, I don't know, 3 to k. We had the sum, and then under the sum we had the ways of how many cycles we had of that length. So we had to choose the first vertex, the second vertex, and the third vertex, and every choice was sort of roughly n vertices to choose from, certainly no more than n. They get fewer and fewer, but never mind. We'll be generous and assume that we have n choices every time. So we had n to the I there, which is certainly no bigger than n to the k. K is our bound, our upper bound for all the little i's now for I cycles. So we had n to the k ways of choosing that divided by 2k, or n to the I divided by 2i, never mind. And each of these required edges was there with a probability of p. So we had those edges to be present, so we had p to the I. And this is now metamorphosing into a p to the k, which is certainly not going to make this smaller. Okay, so by our foresight of choosing p well, let me just copy the half k here. what is n times p? Well, n times p is n to the epsilon. Right? So that's n to the k epsilon. These two are n to the epsilon, and then to the power of k, that becomes a factor up here. So that's n to the epsilon k. Oh, let me write epsilon k. So epsilon to the k or epsilon k. Okay. So that's the expected value of x, its mean. And now we want to use Markov to show that the probability that we have many short cycles is small. Okay, so by Markov, the probability that x do I want strict inequalities there? Doesn't really matter. Okay. So, yeah. Half n is our little a. Sorry. Yeah, no, that's correct. So, right, we want this probability to be small, so that's at most e of x divided by half n. Okay. So what's that? That's at most this. So half times this half cancels with this 2. So that's at most k times n to the epsilon k divided by n. Okay, so did I get this right? Yes, I did get this right. Okay. Now, and we want this to be small, and in fact, we'll show that as n goes to infinity, this tends to 0. Now, why is that? Now it does pay to rewrite this as n to the epsilon k minus 1, because what is epsilon k? It just happens to be less than 1. Because that's how we chose epsilon. Right? Epsilon was chosen to be less than 1 over k. Yeah. So this is going to be less than 1. Minus 1 for the 1 over n is going to be less than 0. So we'll have something less than 0 here. And as n grows, n to the some negative power, no matter what this constant is going to go to 0. Okay? Yeah, goody. But this, I mean, this calculation shows how the choices of epsilon on p of n came about. So we wanted this to go to 0. Right? And we wanted to use Markov to make this go to 0. Now, Markov has to work with the expected number of short cycles, and that is known, that's this. Sort of, it's a little smaller than that, but you can't get any capital out of that, because that's a complicated sum, and these i's are all a bit less than k, but right. So that's there's some. This is not tight, this bound, but it's difficult to get something better out of it. So we need to work with this inequality. So we require this to be this, which is the same as that, to be small enough for this to go to 0. So when we divide this by n over 2, we want to go to 0. And this doesn't look like something that goes to 0 because we have n to the, well, epsilon may be small, but k looks big. But we choose the epsilon to offset the size of k. Even if k is large, and it can be arbitrarily large, that's the whole point of the theorem, we make epsilon small enough to bring this below 1. Yeah, so that's how epsilon, the choice of epsilon comes naturally with a given k, and then, yes, p of n, obviously Erdös already knew this story about 1 over n being the fence on which we're sitting, and the idea of having only few short cycles was probably an abstract idea before the calculations kicked in, but then this is how p of n pops out, namely that n to the epsilon bigger than 1 over n is good enough. That isn't actually that small, right? So root n goes to infinity pretty fast. I mean, it's bigger than log n, right? Okay, so that is most of the proof. Oops. Now, let n be large enough that, and I'll use the next board to write that out. Okay, so we want the expected number of cycles, the probability that, the probability that the number of cycles is at least half n, we want that to be small. Right? We want an n we want a graph at the end of the day that has fewer than half n short cycles. So such that p of the probability that x, the number of short cycles, is at most half n is small. And likewise, where is it? Here. And the probability of alpha to be at least half n to the k is also small. So there exists a graph so that G this just says the number of short cycles is less than half the number of vertices, and alpha of G is right. delete a vertex from each short cycle. So less than half n vertices in total. To obtain a subgraph. Well, this is not going to have any short cycles either because we just deleted them. This is going to have no short cycles. So such that the girth of H is going to be bigger than K. And alpha of H is going to be bigger than order H. Divided by K. Right. I don't need a new board. Hence, what's the chromatic number of H? So we already know that H is a graph with large girth, which is fine. So the chromatic number of H is at least its number of vertices divided by the maximum size of a color class, which is this, right, like this. And that is K. Corollary. For every K, there's a graph such that whose girth is bigger than K, and yeah, you can now choose your parameter of choice that comes with a large chromatic number. So connectivity, min degree, what else do I have on offer? Oh yeah, average degree, let me write it, epsilon, that's a different epsilon, so maybe let's write this. All those are bigger than K. So they all come for free from the chromatic number and from the fact that, of course, subgraphs inherit large girth. By taking a subgraph, you can't create a short cycle. Yeah, okay. Let us distill out of this proof one idea that has taken root since then and become rather ubiquitous. And I've mentioned it informally before. I always used to say that almost all graphs have, I don't know, few short cycles or no large independent sets or large independent sets, whatever. So let me make that precise. So we say almost every and that's the notion I'm defining now. Almost every graph in G and P, where P is it doesn't have to be constant, it can be a function of n just as before. Almost every has property curly P, any property. if, what's the definition of this statement? If the probability that G has P, so that G is an element of this property P, goes to 1 as n goes to infinity. And almost no G in G and P has property P if this goes to 0. Right, now, this is not the almost every that you might know from measure theory. It is not a set of measure 1, because we don't have one single probability space in which all these graphs live. Right, and for a finite space, you can't have probability 0 for any non-empty set. So it's an adapted notion of almost every, but it's important to remember that it's not the same. Then, rather than saying almost every G has this property, we also say G has the property, G, a random graph. So back to our roots, right? This mysterious, just take a random graph. This random graph, element of G and P, has property P almost surely, is exactly that. So rather than saying almost every G has it, we'll say one G, a randomly picked graph, almost surely has this property to mean exactly that. Some people say asymptotically almost surely, which is, in my view, a little doppelgemottelt. Because, yeah, never mind. There are different schools. The Polish random graph theorists say asymptotically almost surely, AAS, and those that come from the, may I call it the Bolabash school. The others say almost surely, and I'm a disciple of the latter, so I'll say almost surely. Some people also just say with high probability, which is sort of very vague, so I'm not such a big fan of that. But you can read that too with high probability. Okay, so it's important to know it's not the same as measure 1. So let me give you a fun little theorem. That is proposition 11.3.1. For every constant, that's important now, P that is neither 0 nor 1, and for every fixed graph H, almost every, or no, let me just write H is a subgraph of G, and this now is the usual subgraph. So an isomorphic copy of H is a subgraph of G. Almost surely. So almost surely your random graph contains the Peterson graph. Anything you like. So why is that? Well, think of G as big. And so you have lots of little potential copies of H. Simply, if you have enough vertices, and H has some number of vertices, say k vertices, right? So as n gets big, you have lots of places where you can try. Now, this graph, this subgraph of G, has certain edges that we want there, and certain edges that we don't want there. So, yeah, I wrote isomorphic copies, so induced subgraph, right? Certain edges that we don't want there. And the probability that all these are exactly as we want them, you can even fix how this H lies on these vertices. And then you have all these edges like K choose true, many edges or non-edges that also all have to be there or have to be absent with some probability strictly between 0 and 1. So the probability that H lies here in exactly this way is some value between 0 and 1. And the probability that it fails to lie there is also some number between 0 and 1. Right? And so in order for H not to be anywhere in G, they all have to fail. But for H order K, there are n over K potential copies. All disjoint. And since they're all disjoint, the probability that they all fail is the product of these probabilities that they fail, that each of them fails. Now, each of them fails with some probability that is less than 1, between 0 and 1, right? So the probability that they all fail is the product of all these things, but this product, the number of factors goes to infinity as n gets big, because k is constant. So you have some constant between 0 and 1, and a power of that goes to infinity, and that product can only tend to 0. So the probability that all these potential copies fail goes to 0 as n goes to infinity. So almost no graph has the property that H fails to be in it. So almost every graph contains H. Yeah, it's a bit of a cheat. The reason this, or the fact that this is a bit of a cheat and works so easily, of course, is just an indication that constant P is perhaps not what to look at. And indeed, random graph theory doesn't look at constant P's at all. Once these things were noticed, people realized, yeah, that's not where the music is. But anyway, we're not going to do random graph theory proper here. So let me give you one more application. Yeah. A property, Pij, is that for all disjoint sets U and W of vertices, so U has to have size at most I, not exactly I, at most I, and W has to have size at most J. We have this property that we studied before. So this is at most I, and this is at most j big, there exists a vertex V that is adjacent to everything in U and non-adjacent to everything in W. Okay. That's just property P, curly P, ij. Proposition 1132 for every constant P, not 0 and not 1, almost every G has, and for all I and J, at least one, yeah, doesn't matter. Almost every G has Pij. Right, you just fix Ij any old way you like, and then for any constant P, almost every graph has this particular property Pij. So let me prove that. What is the probability that for a fixed choice of U and W, there's a good V? Well, it's some number between 0 and 1, that's all I care. Right, so this V has to have all these edges, that's some product of little p's, and times all these little q's, and that is still some number between 0 and 1. So the probability for U and W fixed that there is a good V, sorry, not that there is a good V. I want a fixed V to start with. So the probability that for fixed U and W and a fixed V, the situation is as we wanted. That is something between 0 and 1. Okay, so the probability write this first for fixed U and W, the probability that there is no good V is 1 minus a particular choice of V being good to the power of candidates. So 1 minus P to the U times Q to the W. So with this probability, V is good. With this probability, it's bad. And the probability that they're all bad is that to the power of, how many choices of V are there? N minus U minus W. Yeah. Now, but this is at most one minus P to the I Q to the J N minus I minus J. Now, the only reason we have inequality here rather than equality is that U and W can be smaller than I and J, right? And it's easier for a little v to be correctly adjacent to smaller sets U and W because there are fewer things to satisfy. Also, there are more G's to choose from, so we get this inequality here. The probability that there exist U and W without a good V is at most, well, this probability for fixed U and W times the candidates for these pairs U and W. So how many pairs U and W do we have to consider? Well, n to the I plus J. All right? So, yeah. Times whatever that is down there. So 1 minus P I Q J N minus I minus J. Right. So that's the probability that there's that the theorem fails, that there's a bad U and W. Now, these U and W's, these pairs, they may overlap. So this is a generous upper bound, right? So we're summing over the probabilities that one of them fails, and we can sum over disjoint sets using additivity, and these sets are not disjoint, but that's even worse. So that's certainly a valid upper bound. And now this is a polynomial in n, and this is exponential in n. Right, that's a number less than 1. And these are constants, they don't matter. So this is exponential in this number that is strictly less than 1, so that beats this factor here. So the whole thing goes to 0 as n goes to infinity. And that's it. Okay. So that's this funny Pij, and of course you can ask, why should we care? Well, it has little corollaries. I'll just give you one very striking corollary, which once more bears witness to the fact that constant P is a rather big choice of P. So here's the little corollary. That is 11.3.3. For every constant p in 0, 1, and for every k, almost every g is k connected. Really? I mean, k is a million, right? So almost every g is very, very highly connected. You can choose very highly, and then as n gets big enough, it gets more and more likely. So why is that? Neat little proof. I love this little proof. So proof, can anyone see it? Corollary of that. So we have two vertices, and we want them to be not separable by fewer than k vertices. Any two vertices. Okay. We'll give them k neighbors, which is much stronger than k connected. So we'll show that for every two vertices, there exist k common neighbors. So why is that? Well, these are our favorite two vertices. And make this the set U. And at the moment, let W be empty. Right, then, okay, there exists a vertex. Now I need colors. I didn't bring my colors because I thought I didn't need any. So, there exists a purple vertex that is adjacent to these two, and non-adjacent to the empty set. Okay. Next, put it in W. Then we have x and y here still, and we have this vertex here in W now. Then there exists a vertex for this setup here, which again is adjacent to x and y. It's not equal to W because we put W. It's not equal to the purple vertex because we tucked it away in W. So all I want is that these two vertices are not the same. I don't care whether there's an edge or not. Okay, we put this in there. We have x and y, and we have two vertices in W. And then there's a green vertex. That is adjacent to U and W. And it's neither the purple vertex nor the yellow vertex, and so on. We can do this k minus 1 times. I'd always find a new vertex, and all together we'll have k vertices that are all adjacent to U and W, and they're all distinct. Yeah, that's graph theory at its deepest. Okay, something slightly more serious, corollary not a corollary proposition. So let me give this a special place. Again, for constant p, and we'll show that almost every graph has a large chromatic number. So that's theorem, proposition 1134. You have a question?
Why do we only have to do this thing like 1 times?
Or do it k times, don't care. Right, so 1134 for every p, constant p, I should write that, for every constant p in 0, 1, and for every epsilon, almost every g in G and P has chromatic number bigger than C times n over log n. That's huge. Right, sort of, for naive people like myself, this is almost as big as n. Right, chromatic number for a graph on n vertices to be close to n is really big. Yeah, but then we have lots of edges. So p constant means lots of edges. So it's not that surprising that the chromatic number is big, but this is really quite big. And we can say something about this C as well. C is, 1 over log Q, no, log over, log 1 over Q, okay. Divided by 2 plus epsilon. Okay, so that's all constant, right? Q is constant because P is constant. 2 is constant under its own steam, and epsilon was chosen fixed up there, no matter how small. But yeah, so that's the statement. You might ask, what's this epsilon doing there? And what it's doing there is, if you change it to minus epsilon, then this inequality gets inverted. Right, so that's really the threshold where this happens. That's the theorem of Wallabash, 1988, that if you replace epsilon with minus epsilon, then the chromatic number is no longer big, but it's smaller than this with a revised C. Okay, so let me finish with a little gem. We'll have 4 minutes left. So let's prove every theorem in infinite random graph theory in the remaining 3.5 minutes. There's only one, but it's a sweet one. So G of aleph naught P, product space as before, exactly the same definition as GNP, except we have an infinite product now. What's the measure of an infinite product? Well, you choose finitely many coordinates, and then you take the product to get when you have a brick of finitely many coordinates, you take the measure of whatever the length of that brick is in that coordinate, take the product of all those, and for the rest, you assume that it's the entire space in that coordinate. So you get this finite product to be the measure of any set of this type, finitely many non-trivial sets times all the others, the entire omega e. That's just a handful of possible sets, but for those sets, this measure is explicitly defined, and the rest follows by sigma additivity. So let me write down the theorem now. So that is 1135. Erdös and Rainey, 1963. So for every constant, but now constant makes no sense, so for every choice of p that is neither 0 nor 1, almost every g of g aleph naught p is isomorphic to the Rado graph. Now, almost every now means all but a null set. Isn't that nice? So there's only one countable random graph. Well, that's the Rado graph, or probability neither 0 nor 1. And why is that? Well, same proof as here, right? So a graph is isomorphic to the Rado graph if it satisfies star for every choice of u and w. All right? So we have all these u's and w's to consider, and we have to prove that with that the measure of the graphs for which a bad UW exists is 0. So for a fixed UW, the probability that a particular little v is correctly joined is some number between 0 and 1. The probability that this particular v is not correctly joined is also some number between 0 and 1. The probability that all of the vertices are badly joined is the product of these probabilities, all the same constant less than 1. So the probability that for a fixed UW there is no good v is 0. So the probability for every UW, the probability there's no good v for UW is 0. And so how many U's and W's do we have to cater for? Only countably many. So the probability that there exists a bad pair UW is at most a countable sum, namely the sum of all those possible candidates, sum of all those finite set pairs. And that is 0. And that is sigma additivity. Right? And once more, these sets are not disjoint, but we can make them disjoint. So the sum is still 0. And that's it. So the probability that there's a bad pair is 0. So the probability that every UW is good is 1. So the probability that our graph is the Rado graph is 1.